Hello and welcome to The Explainer. Today, we're going to crack open the statistician's toolkit. We're talking about how to predict things that you can't just, well, count. So how do we go from something as simple as a coin flip to actually predicting the future?
Look, we all get the basics of probability, right? Coin flips, dice rolls, you can literally count the outcomes. But what about things that exist on a spectrum? Like, how would you even begin to calculate the odds of a runner finishing a marathon in exactly 2 hours, 14 minutes, and 13.17 seconds? The possibilities are infinite, and that is where statistics gets really, really powerful.
So it all boils down to two types of variables. On one hand, you have discrete variables. These are the things you can count. The number of heads in 3 coin flips. It can be 0, 1, 2, or 3. That's it. But then you've got continuous variables. You don't count these, you measure them. Things like time, weight, temperature, they can take on any value at all within a range. And that's what we're diving into today.
Okay, so if we can't just count the outcomes, what do? We need a new rule book, a whole different kind of tool. And that tool is called a probability density function. It's the absolute foundation for everything we're about to get into.
Now, don't let that name scare you off. A probability density function, or PDF for short, is really just a graph, a curve that shows you where results are most likely to land. And it has one golden rule you have to remember. The total area under that curve always adds up to exactly 1. Why? Because it represents 100% of all the possible outcomes. The chance that something will happen is always 1. Simple as that.
All right, let's meet our first statistical character. This is the most simple, the most straightforward predictor you can find for continuous events. It's called the uniform distribution, and its whole deal is fairness.
The uniform distribution is built on a super simple idea. Inside a specific range, every single outcome is just as likely as any other. No favorites, no biases. It is the very definition of a level playing field in statistics.
And its probability graph tells the entire story. It's just a perfect rectangle. That flat top? It means the likelihood is constant across the whole range. Any one outcome is just as probable as any other. It's clean, it's simple, and it's perfectly fair.
So where does this level playing field actually pop up in the real world? Well, think about it. If someone's supposed to show up for an exam sometime within a 1-hour window, any minute in that hour is pretty much equally likely, right? Same goes for the exact amount of soda in a can or where a random computer error might happen on an old magnetic tape. Anytime you've got no real reason to expect one result over another, you're probably looking at a uniform distribution.
Okay, on to our next character. This one is a total specialist. If the uniform distribution was all about fairness, the exponential distribution is all about weighting. It's the master of modeling time.
At its core, the exponential distribution is obsessed with answering one big question. How long until the next thing happens? You know, the time until the next customer walks in, or a machine finally breaks down, or that next email hits your inbox. This distribution is the absolute master of modeling the time between events.
And when you look at its shape, it's completely different. See how the graph starts way up high and then just drops off like a cliff? That tells us something really deep about weighting. Short weights are super common, but the chances of a really, really long wait get incredibly small incredibly fast.
And that makes it an absolute game changer for businesses and engineers. They use it to predict the shelf life of a product on a supermarket shelf or the time until a crucial part in a machine fails. It helps them figure out how many people to staff at a call center by modeling the time between calls. It's all about reliability, and it's all about planning ahead.
But here is the really mind-bending part. The exponential distribution is memoryless. Okay, get this. Let's say you've been waiting for an important email for a full 30 minutes. The probability of it showing up in the next 5 minutes is exactly the same as it was in the first 5 minutes when you started waiting. The past doesn't matter. The system basically forgets how long you've already been waiting. It's a super weird but absolutely crucial feature of a lot of random events.
And now, it is time for the undisputed king of all distributions. The one pattern that shows up so often in nature and in society that we just call it normal.
I mean, listen to how the source material puts it.
This is, quote, the most important distribution in statistics. And the reason it's so famous is this powerful idea called the central limit theorem. It basically says that when you take enough random things and average them out, the pattern that emerges almost always starts to look normal.
And here it is, the iconic shape you've definitely seen before, the bell curve. It's perfectly symmetrical. Most of the results are all clustered right around the average, and the crazy extreme results get rarer and rarer the further you get from the middle. This shape just emerges from the chaos all on its own.
So why is it the king? Because it describes so much of our world. Human height, blood pressure, scores on a test, marathon times, even things like family income. All of these are the result of tons of tiny, random factors all getting added up. And the central limit theorem is like this magical rule that guarantees that this adding up process creates the beautiful bell curve.
Now, here's where it becomes a real superpower. We can take any normal situation, like our marathon runner's time, and translate it onto a universal scale. This is called standardization. And what you get is a standard bell curve. Think of it like a universal ruler. By putting everything onto this one standard, we can suddenly compare completely different things, like marathon times and test scores on the exact same scale. It lets you compare apples to oranges.
So, we've just met 3 really powerful characters in our little statistical story. Each one has a very specific job, and each one gives us a unique lens to see the world through. So let's bring it all together.
All right, let's do a quick recap of our 3 characters. First, you've got the uniform distribution, our flat rectangle, and it's all about modeling total fairness. Then there's the exponential distribution, with its steep decline, which is perfect for mastering the weighting game. And finally, you have the king, the normal distribution, the iconic bell curve, which rules over averages. These aren't just abstract math ideas, they are real, practical tools for making sense of a messy world.
Once you know these fundamental shapes, these patterns of probability, you start to see the world in a whole new way. You can spot the order hidden inside the chaos. So the question I'll leave you with is this. Now that you know what to look for, what hidden bell curves and weighting games and moments of pure fairness will you start to see in the world around you? Thanks for watching.